Hello. Hello. Can I start? Okay, fine. Let me start. Okay, fine. Okay, good evening, guys. So, welcome to our third session here. This third session, we are going to discuss 2017 uh, question and answers for ISRO, that too for manufacturing. In 2017, uh, with manufacturing and production, two questions. No, one question has been asked from industrial engineering. Okay, so we'll discuss that question, and all the questions are from manufacturing and production. Okay. So in the previous two sessions, we have completed 2015 and 16. In 2017, we have set 1 and set 2. Okay, so this is set 1. Okay, let's proceed. First question here says, the metal removal rate in abrasive jet machining process is high, very high, low, very low. So in the previous class or in the previous session somewhere, we have discussed. Okay, 1 minute. So we have discussed the abrasive jet machining, right? I think so. We have discussed ultrasonic. We haven't discussed the abrasive jet. Okay, abrasive jet is nothing but we have pressurized air. So there is some kind of a nozzle like this, right? There is a nozzle and some pressurized air plus pressurized air plus some abrasive particles are forced through this nozzle. This is a nozzle, right? So, and this is the workpiece here. And as these abrasive particles are hitting the workpiece, so each particle will have some mass. And of course, because of the pressurized air, the nozzle will use the pressure and get converted into the kinetic energy. Nozzle is used for converting pressure energy into kinetic energy. You know that, right? So the pressure is converted into kinetic energy. What is kinetic energy? Increasing the velocity, right? Pressure is being converted into velocity. Velocity is being increased. Whose velocity? The particles' velocity are being increased. So mass into velocity. Mass of particle and velocity of the particle are being increased. So if you have, this is called standoff distance, right? This is called standoff distance. The distance is maintained to make sure that the proper material removal rate is taking place. The standoff distance should not be too high or too low also. I'll tell you the reasons, but let's see the material removal rate for here. Okay. So if you have some mass of the particle, and all these two are particle velocity and particle mass. Okay. So as pressure energy is converting into the kinetic energy, velocity is getting increased. That velocity, mass into velocity is what? Moment, right? That moment, the momentum is coming. The particle momentum is hitting the workpiece as with high velocity with good mass. It's being hitted with the workpiece. What happens? There is some kind of a material removal rate that is happening on the workpiece. So some kind of material is being removed here because of the denting action. Okay. So generally, abrasive jet machining is used for some kind of hard materials to machine. Okay, this is a non-traditional machining process, right? So here they're asking whether the material removal rate is high, very low, very low. it cannot be high. That is for sure. Why? Because it is a slow process. It is very slow. Because of the slow process, you cannot have that high material rate. So first option is wrong. Very high to forget. High only is not possible. Why? How very high will be possible? No. So these two are striked out. Not possible because it's a slow process. Right? This is very slow process. But this is slow compared to conventional. Compared to other non-traditional machining process, it might be faster. But I'm telling about this abrasive jet machining compared to some kind of a conventional machining. Why at all we are using this abrasive jet machining? Why we are using this non-traditional machining process? Because whatever the procedures that are, whatever the machining, hard to machine things are there in traditional machining, we are using this non-traditional machining. Okay, some, let us say if you want to drill a hole, very small hole in very big item. Let's say if you have some kind of uh, some kind of blade, right? In that blade, you want to have a micro hole, right? So how do you make that micro hole? So this will be aiding this micro cutting action. Okay, this abrasive jet machining will be adding some micro holes. Will be able to make this micro holes in the very difficult to machine materials, like very hard and, for hard and brittle materials, right? So if you have very hard and brittle, it's very difficult for us to machine in a normal traditional machining process. Then that too very micro holes, right? Micro holes, very difficult, right? So we can do that. For these things, this abrasive jet machining will be used, right? So obviously it is a slow process. Because of that, high material removal rate is not possible, and neither it is not low also. It's not very low. It is low actually. Okay. So generally, if you go and talk about the disadvantages of abrasive jet machine, is this low material removal rate only. So disadvantage of abrasive jet machining, disadvantage of abrasive AJM, they say, is what? Low MRR. This is one of the reasons. That is the first thing that you discuss actually. And there are some other advantages, but yeah, this is one of the advantages. So abrasive jet machining will be having low material removal rate. Please remember that. Okay. So there are some other non-conventional machining process like ECM, EDM, USM. So slowly, as and when we proceed with some questions, already yesterday we have discussed something about ultrasonic machining, right? So today we are discussing about abrasive jet machining. In the coming sessions, maybe they might be asking something about laser beam machining, or maybe some kind of electric discharge machining, electrochemical machining. There are so many machinings. So based on the questions that they have asked, we'll be discussing. If at all we are discussing, as this question is from coming from non-traditional machining process, we cannot completely discuss. It's going to take time. So if information is needed, please do ask in the chat box. We'll be providing it. Plus, please revise all the concepts before attempting the question. So I'll tell you one thing. So you might be watching this as a live video, or maybe you are watching this as a recorded video. My suggestion is that don't directly watch this. First, you take the paper, solve. First, to revise the concepts, then take the paper, previous year paper. Maybe this is 2017 first paper, right? Set one. Take this, solve all the questions in manufacturing. Already, all the questions have been given to you by the institute itself, right? So segregate it. Try to solve. Then assess yourself by watching these videos. Okay, that is a good way of doing. Directly watching this video will not give you anything. Okay, please try to do. Then you might fail in something and then learn it. Okay, that is the way that I would suggest. Okay, good, fine. Next. So the source of energy in ultrasonic machining is. So yesterday we have discussed why we are not why yesterday, in the sense like the previous class, we have discussed why the ultrasonic machining is performed. Okay, so let's see none of this will remove electric spark. So who is using, which machining is using electric spark? Electric discharge machining will be using electric spark machining. EDM is using electric spark because of the sparks only, right? So if all this material, if you go and revise the electric discharge machining, how does it work? So you have some kind of workpiece, and then there is a tool, which is both workpiece and tool are to be electrically conductive. Then you submerge these two in the dielectric fluid. Dielectric fluid is some kind of some different kind of kerosene. Okay, you submerge this thing, the tool and workpiece, into this dielectric fluid, and maintain a gap between workpiece and tool. This is tool and this is workpiece. There's a gap that is maintained, right? So that gap is maintained by servo mechanism. Okay, with it on all, you can revise and come back here. Okay, so this is tool and this is workpiece. Okay, so then now what happens, as this is submerged, as you try to pass electricity to this gap will try to get the potential. It needs more and more potential as and when you're trying to increase the voltage. This is a high voltage process. As and when you're increasing the voltage, at certain point the dielectric will break down. As the dielectric is breaking down, what happens, there is some kind of a spark momentarily generated. That spark is having high amount of temperature. That temperature is leading the workpiece to melt, and in that small fraction of time, high amount of temperature, huge heating is happening, workpiece is melted and then evaporated. Like that, continuous sparks will be provided, and hence material removal rate is happening in the electric discharge machine. The same way, electrical and chemical source is used for electrochemical machining. Even EDM also will come here. Electrochemical machining. So this is some kind of a chemical machining where you have some chemical that it's called electrolyte, sodium solution, right? NaCl and all will be added into the water because of some chemical reaction that is ignited because of the electricity. You have this machining happening. Okay, so that is what is electrochemical machining, and this is example is ECM, right? So obviously the answer will be mechanical energy, where you have some kind of a machine like this, right? So this is your ultrasonic machining, right? So you have some kind of a transducer, and you have some kind of workpiece, and this is abrasive slurry here. You see, this is your abrasive slurry, and some pump is being footed here. It is putting the abrasive slurry between, and this is your tool, and there is some kind of vibration that is happening because of the transducer coil. Yesterday we have seen how there is an ambiguous question that has come in the previous paper. What happens to the MRR if the time is progressing, right? Something question was there, which was very ambiguous. So, but we have answered that it increases and decreases. The MRR will increase and decreases. That is what has done. We have discussed about USM yesterday, not in the previous class. Okay. So here, as this vibrations are happening, this vibration is getting converted into this vibration energy is given to this abrasive particle. The abrasive particle is getting momentum and is hitting the workpiece, and here the workpiece will be brittle or some kind of very harder materials. So example, we can machine ceramics, which are not electrically conductive, right? So that's what make the ultrasonic machining different from the other two machining processes, that is ECM and EDM. In ECM and EDM, both the tool and workpiece need to be electrically conductive, but here in ultrasonic machining you are trying to use mechanical energy only. It's an impact that you are pushing through, right? So impact is coming from these vibrations to abrasive particle to workpiece. That impact is happening, and then brittle fracture is happening, and material removal rate is happening. So it is mechanical energy. Okay, good. Next. So I saw some isometric projection of sphere. This is for your first year engineering drawing question only. Okay. So what is isometric view? Isometric view is nothing but you have top view, front view, and bottom. The top view, front view, and side view, right? So isometric view is like somewhere you have some angles made, right? Like you have some axis, this axis, and this axis. So some sphere is placed like this, right? So this is your sphere, right? Sphere. So be it in any view, top view, front view, what view, isometric projection of sphere is circle only. It looks like a circle, isn't it? Any view you see, It looks like a circle. That's a simple answer. Very simple question. Isometric projection of sphere is circle. But how does this ellipse and hyperbola and parabola form? Those are conic sections actually, right? In conic sections, you take a cone like this, right? You take a cone like this, and you cut it. This you have this thing, right? If you take something like this, right, and if you cut it like this, then there is an ellipse formed, right? And if you are cutting in different angle, how do I say that? Yeah, just something like this, right? Then you'll get some kind of a parabola, some parabola like this. And if you're cutting it something like this, then you'll get a hyperbola, right? So like this, in conic sections, you'll be able to discuss, you'll be having this ellipse, hyperbola, parabola, whatever it is. But here they're asking simply isometric projection of sphere, that is circle. Very simple question, very easy to answer. Okay, hardly will take 1 second or maybe 5 seconds. Okay, next. It is required to connect two parallel shafts, the distance between whose axis is small and variable. They can be coupled by. Okay, so here the two parallel shafts they are saying, right? So forget about the question. Let's discuss what is universal joint, knuckle joint, sleeve joint, and Oldham couple, and then we'll come to the solution. Then we'll come to the answer. First is we'll discuss what is what. Okay, so if you see the first one is your universal joint. Universal joint. Okay, what is universal joint? You see, this is something that we have put here, and it is having moment in different directions. If you connect one shaft here, if you connect one shaft here, another shaft here, right? If you have one shaft here, obviously these shafts are not parallel to each other. They are saying parallel shafts. That is a question that you have to understand. So for universal joint, the shafts can be parallel. Sometimes it can go to different angles also. There is an inclination that is happening. There is an angle theta here. So it is no, it's not for parallel shafts. What I'm trying to say here is, okay, it's not parallel shafts, right? So generally the axes are inclined to each other. So I can say axes are inclined to each other. Right? And the next is knuckle joint. What is knuckle joint? Generally, knuckle joint is used by two rods. See, rod 1 and rod 2. So it is done with some kind of a bolt here, right? Some kind of an intersection point here. And again, this is the axis here, this is the axis here, but this can be parallel, but as it can rotate about this, it can rotate, right? So again, the shafts cannot be parallel. And this generally knuckle joint is used some in some cases where the rods are the connecting rods should will be under tensile load. Okay, so I can say that connecting rods will be under tensile loading. Okay, and the next one is sleeve coupling. It's also known as muff coupling. Okay, sleeve or muff coupling. Okay, sleeve or muff coupling. So what is this? So here you can see there are some kind of slot that is made, slots. So these are used for parallel shafts. So this can be the answer. But in question they gave one more thing: the distance between whose axes are small and variable. See, parallel shafts means shaft 1 and shaft 2. Good. if the axes are aligning to each other, okay. But here in this question, they're expecting some offset between the shafts. So this is axis 1, axis 2, there is an offset here. So that is what the question is. So the highlight of this question is not the parallel shaft, it's the second one that is coming to picture, where the distance between the axis is small and variable also. The offset they're talking about, right? So here the axes are parallel. Yeah, I'm happy with that. But here the axes are aligned to each other. So that is why this is not the answer. Okay. So of course the coupling is used to connect two shafts where these are aligned to each other, but the distance between the shaft is not variable. Okay. But here, yes, this is what is called Oldham coupling. We might have seen this thing in our theory of machines as well in the mechanisms, right? Oldham coupling. And this is the answer for your question. What is that? You have some kind of two parallel but not collinear shafts, right? So this is the axis here, and this is the axis here. So this is the axis, this is the axis. These are all having some offset, right? So because of that, here also you can see this is axis, this is another axis. Sorry, let me draw it neatly. We write it here and here. Both are same diagrams, but one is a little rendered 3D thing. That's it. This is what is this? Is offset here also. So if you go and draw like this is your offset. Offset. See, the offset is coming here. Offset. Okay, so that is what they're asking. Obviously, this is the answer, which can accommodate some small variations, like, and also this offset can be controlled with these slots. This slot, you see, the offset can be controlled, whatever the, and it is not very high. It is only small variation is allowed, and hence, obviously, the question that they have asked is parallel shafts. These are parallel, of course. These are parallel to each other, which are having some offset. And of course, this is the answer. So, answer is Oldham. Good. Let's proceed. Okay. And next is variety of cast iron which has maximum hardness. Oh my god, this is like we have to know so many things about irons. Okay. So gray cast iron, malleable iron, ductile iron. So it is full of different irons that we are going to discuss today now. So let's forget about the maximum hardness. First, we will discuss what is gray cast, malleable, ductile, white, and then we'll discuss about the properties of that. Then we'll pick the right option from there. Okay. So first, what is gray cast iron? Gray cast iron is nothing but the iron which is having carbon in the form of graphite flakes. I'm writing it. Simple short answer is in gray cast iron, carbon is present in the form of graphite flakes. If you go and form of graphite flakes. Okay, so there is a standard question that has asked that has been asked in gate for mechanical. So people generally often make a mistake. They think that gray cast iron will expand upon cooling. No, it will expand upon cooling only in solidification state. Okay, liquid state and solidification. In solid state, again it will contract, but the overall contraction will happen. So that is a misconception where people carry it. Gray cast iron at the end it will come upon cooling, it will compress. Upon heating, it will expand. But during solidification, during cooling, during solidification, in the liquid phase and solidification phase, it will expand. Okay, so now why it is called gray? The color gray is given because when you fracture this gray, when you try to pull and try to make put some load on it, if it is fracturing, the fracture will look in gray color. That is the reason why gray cast iron. And it is having hardness, right? Gray cast iron, whoever is having good carbon content, will be hard. But okay, I can say it is hard only. It is not. We can say it is hardness is good. You can say that, but it is not comparable with some other option here. That's why I'm not writing this is the option. Okay, and next is malleable iron. What is malleable iron? Malleable is some kind of an um, this carbon is presented in the form of some kind of irregular nodules of graphite, irregular shaped graphite. Irregular shaped graphite is present in the malleable iron. Okay, but generally this also is not very hard, but it is having some kind of improved toughness and ductility. Okay, I can say irregular shaped, irregular shaped nodules of graphite and improved ductility, or you can say improved toughness. Not even ductility, I can say toughness. Ductility also is there, but yeah. And what is ductile iron? Ductile iron is nothing but spheroidal graphite iron. It's also known as spheroidal graphite iron. Spheroidal graphite iron. All are having graphene, graphite. You can see graphite iron. It is ductile because it's highly ductile in nature. Okay, because of this spheroidal graphite. It has the hardness is very less here. Okay, less hardness. Ductile by name itself, we can say. Right? Yeah, and the last one is white iron. White iron is some kind of uh, same thing because of the fracture is looking like a gray color here because of that gray cast iron. White iron also is because of the fracture will look like some kind of a whitish in color because of presence of iron carbide. That is because of presence of cementite, right? Presence of cementite, Fe3C, right? Presence of cementite. And of course, this is very hard in nature. Hardness is high. Okay. So upon all these comparisons, I can say white iron is having good hardness compared to the other three options. That is gray cast iron, malleable iron, and ductile iron. Okay. Good. Let's go to the next one. The crystal structure of cementite is, okay. The crystal structure of cementite is nothing but, what is cementite? Previous slide only we have seen cementite. This is Fe3C, right? Cementite is Fe3C. Yesterday or in the previous class, we have seen the cementite Fe3C. It is having so much of carbon content, right? So it is some kind of carbon and iron, isn't it? Yes. So yesterday we have seen some different phases, right? The alpha Fe, right? Beta Fe, but beta we told it is not having, the beta has been removed because in the literature they found out that they found out at 727 degrees centigrade they found out there is some change happening, but only magnetic properties are changing but crystal structure is not changing. Initially they thought that something is changing and they gave beta iron, but after few research, I mean after few years of research, again they found that nothing crystal structures are not changing, but rather magnetic properties are changing at 727 degrees centigrade for the iron carbon diagram. So there is no beta, only gamma is there. That is gamma iron austenite, right? This is ferrite austenite, and oh, sorry, this is ferrite. So this is ferrite, right? This is austenite, right? So this is BCC in nature, body center cubic. Yesterday we have seen, and this is FCC in nature. BCC is body centered cubic, FCC, face centered cubic. And the question what they've asked here is semantite. They're saying it's orthorhombic. Orthorhombic. Orthorhombic, what is it? There are some 12 type of crystal structures. Orthorhombic is nothing but you have some kind of like this and some kind of plane like this. You have some kind of angular this thing. It is not straight. That is what is orthorhombic. Okay, and they might be asking one more question. The Martin site also very important question. Martin site is which in which structure? Martin site is very hard in nature, and it is body centered tetragonal. Body centered tetragonal. They might be asking this kind of question also. Body centered tetragonal. Tetra PCT. PCT. They say. Okay, so according to this question, the answer is D, or is orthorhombic. Okay, orthorhombic. So the tetragonal we didn't discuss, right? The tetragonal some kind of square edge, but of course it is not for some point orthorhombic. Okay, so the difference between tetragonal, the angle between here is 90, but here it is not 90. That is the thing. Okay, next one. Hardness will be highest after which of the following heat treatment process? Okay, hardness will be after higher. So we will see what is furnace cooling, air cooling, oil quenching, and water quenching. Okay, so what is furnace cooling? In yesterday also we discussed. This is nothing but annealing. Annealing, right? The main aim for this furnace cooling, what is furnace cooling is nothing but you keep your object in the furnace, heat it for some time, then switch off the furnace and don't remove the furnace immediately. Wait some time so that the inside furnace only this object will be cooled along with the furnace. It will take so much time to cool. That is what it means, right? And hence this annealing will reduce hardness and increase ductility, right? Reduces hardness and increases ductility. Okay, air cooling is nothing but normalizing. Because you put it in furnace, switch off the furnace, immediately open the furnace. Sudden cooling, air. The faster cooling rate. The rate of cooling is very faster here compared to the furnace cooling. So this is medium hard. Hardness is in medium range. It's not very hard. See, please remember the thumb rule is if temperature gradient is very high, if DT is very high, temperature gradient is very high upon cooling, if your temperature gradient is very high, it is hard. Generally, it is thumb rule. Temperature gradient is very low, then annealing. Slow cooling, soft product. Very fast cooling, hard product. Next is oil quenching. It's nothing but you instead of air, you are putting it in oil. Okay, because of that, it is harder only, harder, but not compared to water quenching. Is good. This is good. And here, highest hardness, water quenching. Just put it in water because temperature gradient is very high here now. Highest hardness. So what is the order here? Cooling rate A hard less than harder, B less than, C less than D. This is increase in hardness. That's it. Okay, so the answer is D. Okay, good. Next, which of the following heat treatment does not improve hardness? Here only we have seen previous question only. Here we have seen annealing is reducing the hardness and improves ductility. Simply we can directly go. Quenching is not at all option. We discussed right now. Water quenching and oil quenching will improve hardness. Here they are saying does not is very important. Cyaniding will improve hardness. Yesterday also we have seen cyaniding. We are putting it in a propyl or methane environment for some time, and then we are doing that coating, that surface coating, surface hardening we are doing. That is cyaniding. Obviously, it is also for improving hardness. Between these two, obviously this is more softer than this is medium hard, medium hard. Yesterday, now just now we've discussed this is medium hard, right? Simply, I don't know, these are related questions, I don't know why they have given. Simply I can go ahead and simply directly I can put the option as D. Simple, easy, very easy. Once you know this concept, you can attempt this. If you know this concept, you can attempt this. Okay, good. Very easy, very easy. Next, the relationship of shear angle with the yesterday we have seen. That is this shear angle. Yesterday or in the previous class. Yesterday, simply is yesterday in the sense like in the previous class, because the previous class has happened yesterday according to this time what I'm recording here. That's why I'm saying yesterday. Yesterday means previous class. Okay, please do not get confused with that. I'm sorry for that. And here beta is friction angle. What is friction angle? It is tan inverse mu. We have seen yesterday. Mu is coefficient of friction between tool and rake, tool and workpiece. Alpha is rake angle. Right? So the relationship between beta, alpha, and phi, there are some theories that have been developed. First, let's discuss the theory and come back to the question. Okay, let's discuss the theory. There is first thing called Merchant's first analysis. Okay. Merchant's first analysis or first theory. Okay, so that is um, Merchant's first theory, first analysis. Merchant's first analysis. It is like to this had a background of minimizing the power for minimum power. They did some analysis and did for minimum power and did some derivations. Let's not go to the derivation. If you want, you can go and read in the books. This is for minimum power, and they found out that 2 phi plus beta minus alpha is equal to 90 degree. Here they're asking phi, right? Phi is equal to, just send 90 degree. Instead of 90 degree, I'll write pi by 2. Okay, for our convenience here. Pi by 2. So divide 2 on all the sides. So it is phi is equal to pi by 4 minus 2 beta plus 2 alpha. Is it the option that they're looking for? No. 5 minus 5. So pi by 4 minus beta by plus alpha by 2. So this is not the option. Right. The second is analysis 2. Merchant's analysis 2. Second analysis or analysis 2. Right. This is again some modified. So this is derived. This is empirical. The empirical relation is given as 2 phi plus beta minus alpha is equal to cot inverse k, where k is some machining constant. Machining constant. So obviously they have pi by 2, so this is not the answer. Okay, so two theories are done. Next is Lee and Schaffer theory. So this is based on slip line field theory. Based on slip line field theory. Okay, so they say that the slip lines will meet at 45 degrees. The maximum shear plane is in 45 degrees to the loading. Like that, they have some analysis. Let's not go into deep. So here they have derived that phi plus beta minus alpha is equal to 45. That is pi by 4. Okay, so if you see here in the this thing, it is pi by 4 minus beta plus alpha by 2, right? So wait a minute. There is this, yeah. So what am I making? What is it? Al pi minus beta plus alpha by 2. Okay, so who is not there here? Stabler theory. So Stabler theory is modified Ernst merchant theory, and this will give you phi is equal to pi by 4 minus beta plus alpha by. This is modified merchant's theory. Okay, this is the answer. Okay, good. Next, this you have to remember. But people mostly use this in the exam. Something yesterday we have used this theory, if you remember. Yes, we have used it. Okay, good. These all are formula based questions. I think you should remember the formula because you cannot derive this in examination, right? So if you're going for the economics of machining, okay, so they're asking that optimum cutting speed for maximum production. Right? So this cutting speed and all will come from this Vt power n is equal to constant, right? This Taylor's two-life equation, right? So the problem here is there are two problems. One is maximum production, and another is minimum time, minimum cost. There are two, things that are done, right? Two cases. One is maximum production, another is total minimum cost. I'll write the formulas. Hopefully, you'll get all these formulas in the notes that you get from the institute. But see, first I'll write for the maximum production. So that is for maximum production. Sometimes it's known as maximum production rate also. So what you have to do, you have some times. Machining time T is equal to the two lifetime T is equal to machining time plus idle time plus Tm by machining time into tool changing time. Like this we'll do. So then we have all these things as a function of v, function of velocity. V is velocity here. Okay, please remember this, right? Then we'll do this dt by dv is equal to 0. If you do this, you'll get the formula, that is v optimum, velocity optimum is equal to c by 1 by n minus 1 into tc, tool changing time, to the power of n. T optimum is equal to 1 by n minus 1 into tc. So the question they have asked is this. You have to remember this formula. There is no other option. Okay, c and n are where we have c and n. This is two life exponent and this constant c. Okay, so if you see here, c instead of c they have put k. Okay, so c by 1 minus n by n, 1 by n minus 1 into tc. So 1 by n minus 1 into tc. So option is b. B is the option. Like that, there are other formulas. Remember, this is for maximum production, right? Then we have another thing that is for uh, minimum cost. Minimum cost. Minimum cost, not E. Minimum cost for total minimum cost. Okay. Okay. Here also we have some cost, total cost C, and then we'll divide this total cost C with, we'll differentiate with respect to velocity V. So this is total cost C, and this is velocity, cutting velocity, right? So, good. So we can say from this derivation we get V optimum. It's a very big formula. It is C divided by CE by CM, right, plus TC into 1 by n minus 1 to the power of, okay. So please remember this is V, sorry, C two like equation, Vt power n is equal to constant. Okay, this is the formula. Well, very important formula. Okay, next. Next is the side relief angle in a cutting tool signature of. So first you have to understand which tool signature they're talking about. There are two systems, ASS system and ORS system. But generally people ask, here again the question is ambiguous, okay? Okay. Of course, there are some side relief angles in orthogonal system also. Maybe there is nothing like that. But be pretty sure that which system they're asking for. So the system they're asking for, American Standards Association, that is ASS system they're asking. So in ASS system, first we have to understand how the tool signature is being represented. Right? So the tool signature for ASS system, tool signature for ASS system, let me write that and then write what is what here. Right? So that is for ASS system, let me write it. Right? So if you see, that is back rake angle. So I'll tell you one hint better. You make couples, one couple, two couple, third couple, and one bachelor. Okay, this is couple, couple splitting into couple, right? Every second option for every couple, the second one belongs to some letter S, subscript S, subscript S, subscript S. First couple belongs to alpha rake angle. Second couple belongs to relief angle theta. Third couple belongs to cutting edge angle C. And last bachelor will belong to radius R, nose radius R in the tool. So I can write here back rake angle, side rake angle, end relief angle, side relief angle, end cutting edge angle, side cutting edge angle, and this. So this is how I remember. If you want, you can also remember this. Three couples, first couple alpha, theta, C. Rectangle couple, relief angle couple, and end cutting edge couple. In each couple, the second one belongs to side, side, side. And the first one you can fill automatically. And that is what is this. And there is a bachelor that is there, that is nose radius. Okay. So this is a tip. You can remember if you want. If you have another memory tips, fine, no problem. Let me remove all these things. Right? Dash, 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 dash. Right? Now, what is the question given? Let us write that. They have given 10 dash 20 dash 7 dash 6 dash 8 dash 15 dash 2. So they're asking side relief angle. Theta is side relief angle. So this is side relief angle. Theta is side relief angle. So answer is C. So let me write what is what here. alpha b back rectangle. Alpha is side rectangle. End relief angle. End cutting edge angle. Side cutting edge angle. Cutting edge angle. And R is nose radius. That's it. Okay, this is how you have to remember. If you remember the signature, 1 minute answer. Okay, next. The missing distance between A and B. Okay, they're asking the distance between A and B. Okay, so if you want to have the distance between A and B, you can take it from here. Okay, this is 45, right? So it's a very simple question, but I can attempt it in any way that you wanted to have. Okay, so what is that? So you can say that the uh, okay, let me do it in this method only. What is this thing? So what is the maximum distance? 45 pi, 45 point, 45.5 is the maximum distance that this total rod can have. Okay, so let's take this. So like this, do this. Okay, let's not draw it because it will take time. So let's say here, this is 45.5. Okay, and so they're asking the missing distance between A and B. Okay, so if you want to calculate from here this side, right? So if that has to be missed, obviously you can take the minimum distance here. So 30 minus this thing is 29.8. Okay, and from here also I can take the minimum one, that is 13.2 minus 0.5 is 20, sorry, 12, not 20, 12.7. Why I have taken minimum there? Because they're asking the missing distance. So missing distance also is having some kind of error, na? That's why. Okay. So if you say that, sir, this is not making sense, then we can go for that tolerancing yesterday. We have discussed, no? We have discussed in the previous class about the tolerancing of the density. Right? The tolerancing of the density we have discussed, isn't it, yesterday in the previous class? Right? So we can even do that, no problem. If you have any confusion with that, okay, let's do that only. Let's not do all this distance because this will be a little not a straightforward thing that we are doing. Let's do the overall tolerancing thing. Okay, what is this? This is the 45, right? And this is the 30, and this is the 13.2. First, we can calculate what is the difference between these two. Okay, so what is this? Obviously, this distance minus this distance and minus this distance will give you this distance, right? So I can say 45 minus 30 plus 13.2. Okay, this plus this is here, and 45 written it. How much you'll get? So this is 43.2. 45 minus 43.2 is 1.8, right? So this is what is this. Then we have to add the tolerances as well. Yesterday I have told you plus or minus is there here, right? Yesterday when we have derived this thing, we have seen that delta m by m minus we removed and we have put plus for 2 delta r by r plus 2 delta l by l. Yesterday we have seen this. This is also the relative error propagation, right? So here also the error has been propagated. So we are adding the error as well. And what is the error? 0.5 is error here, plus 0.2 is the error here, plus 0.5 is error here. So This error plus this error plus this error will give you how much? 1 plus 2, 1.2. So that is what is plus or minus 1.2. That's it. We can add the errors. That is the error of propagation method. Okay. So let's remove all the stuff here. So the answer is this. Error of propagation. Error of relative error propagation, not error of propagation. Relative error propagation. That is a method. Relative propagation error. Okay, good. Now, so some this I mean it seems 2017 they are not asking big questions like in 2015 and 16 because those are very calculation intensive. Here I'm not seeing any calculation intensive questions. Okay. Okay. The method of development of right regular prism is okay. For this, I have put one diagram, so I can draw these diagrams. I have put one diagram. So these are used for the developments of some constructs. Like for some geometries, there are some developments we can do. So if you see the first one, the parallel line development is the first one. In parallel line development, you can see that they use some parallel lines. These are all parallel lines, isn't it? 1, 2, 3, 4, 5, 6. These are all some parallel lines where the where this method, whatever the parallel line development method, is surface which is consisting this parallel lines. So surface 1, surface 2, surface 3, all are having parallel lines. Here also it is parallel development only, but cylinder. All are parallel lines only. Only the edge is circle here. So these two are parallel line developments. Okay, and the second one is the radial line development. What is this radial line development? There is a central point here, and it is going to some other points like this. So using radial line development, the central line is to construct to when it will try to go to some expanded patterns. Whatever single point, central point, this is central point to three-dimensional space. So this is a three-dimensional thing. Okay. So example for the radial line developments are cone and pyramid. So you can see like a cone and pyramid. So this is a pyramid actually. The cone is in the next one. This is pyramid. Here also there is a central point. See, central point. Right. So this is cone. Sorry, pyramid, not cone. This is pyramid. And this is cone. Okay, and for very complicated structures, it's very difficult for us to construct. That is called the triangulation method. This is what is triangulation method, and the example for this are tetrahedron and other some polyhedrons, right? Tetrahedrons or some kind of a polyhedrons. Okay. And sphere is some kind of an very complicated structure to represent with the help of lines and all these things. So as we cannot represent it with straight lines and all these things, so it is approximate development, and that's why this is called approximate development sphere. Okay, so let's go to the question. They're asking the development of regular prism. Prism is some kind of a pyramid only, right? Prism is some kind of a pyramid, isn't it? So hence it's no. Prism, sorry, prism. This is pyramid, right? Prism is parallel line development. Clearly, we can see this is prism and parallel line development. Simple, right? Regular prism is parallel line method. Simple question. And write radial is cone and pyramid. Triangulation is for tetrahedron, and approximate method is for sphere. That's it. Okay. Next, below the ductile to Dreidel transition temperature, weld joint shows. This is a very good question. This is a very good question. Okay. So it is not belong. Actually, this is welding question, but it's mostly the understanding of stress strain graph. So high ductility, high toughness, low toughness, ductile fracture, all these things will come from this stress strain graph only. It is all about material property, right? So let's do that and see what is the question they have been asking for. Okay. So if you see here, right? Right? This is the fraction. Ductile and brittle. So this is for ductile material actually. You can see that yield phenomenon in ductile material. Ductile, it is ductile. Okay, I'm not telling about material, but let's say it's ductile. For brittle, this is this. It will go and fracture, 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 very fast fracture. The text belongs to fracture. Here, no yield. In brittle, no yielding is there. So obviously, for high ductility, they are saying ductile to brittle transition. So ductile to brittle transition, there is no time chance of ductility. Wrong option. High toughness will have, what is toughness? Area under shear, the stress strain curve. This is stress strain curve. Area under stress strain curve till fracture limit. This is what is your toughness. Okay. So this is high toughness is for ductile, not for brittle. They're asking for the brittle transition, right? This also is not option. So low toughness is the answer. Ductile fracture will have to happen at high toughness only. So that is not the answer. Okay. So this is how you have to answer. It's a very generic and basic question that they have asked. Hopefully you'll understand this. Okay, good. So next. In continuous casting process, the mold is generally made of, what is continuous casting? You keep on pouring it, keep on pouring it, it will keep on pouring it, and it will get solidified. So here some pouring will be happening, and it will pass through that runner, and all these things it will go. And at some time, at a certain point, it will solidify, it will cut off again, it will coming, it will cut off again, it will be coming, it will cut off. This is continuous casting. You will not have any interruption while doing the casting, right? So they're asking, the mold is generally made up of. Generally, mold is made up of molding sand and all. But here they're asking whether if you are using a material, which material is useful. So for molding sand, the molding material, one property that is very important in terms of casting, the mold material should be having good strength, neither high strength, low strength, medium strength, where it should be able to hold the liquid material, and also you should be able to destroy the mold cavity after done. But in continuous casting, no need of destroying it because it's continuously coming, right? So forget about strength. So we can talk about heat transfer. So heat transfer should be good. Thermal conductivity should be good. So what I can say is that mold should have good thermal conductivity. In which of the following option we can say which is having high thermal conductivity, we can go there. So cast iron, yeah, it is good for some kind of casting and all, but compared to bronze and copper, the cast iron is not having good high thermal conductivity. Bronze, what is bronze? It's an alloy, right? Bronze is what thing? It's an alloy of what? Of course, in bronze also we can have, it's an alloy of copper and I think it is tin, yeah, copper and tin. So copper is having good thermal conductivity, but tin also is having. But compared to copper, bronze is not high thermal conductive, right? So yes, copper is the answer. Tungsten is harder, but compared to the thermal conductivity, tungsten carbide is not having good thermal conductivity compared to copper. So in continuous casting process, copper is the material that is used for the molding material because of the excellent thermal conductivity factor. Property, I can say. Okay, because the efficient heat extraction will happen for efficient heat extraction. For efficient heat extraction and maybe solidification of the molten metal. Okay, good. Next. Which one of the following steels contain least percentage of carbon? Ha. So steel are having different steel, right? Alloy steel, carbon steel, that steel, low carbon steel, high carbon steel, right? There are so many steels. Silicon steel. Yesterday we have discussed. There is some other steel. What was that? I don't remember what was the steel. Silicon steel is used where? Yesterday we have discussed in the electrical industry for the transformers because it is having high magnetic permeability, right? And then we have so many steels. Okay, so here in mild steel, you have the carbon content is around some 0.3 percentage. Okay, they're asking for the least carbon percentage. So here it's approximately 0.3 percentage of carbon here. Here it is approximately some 0.03, something like that. And here also it is approximately 0.03 only. But for IF steel, yeah, somebody has joined, Himanshi. Good evening. Good evening, Himanshi. So here, please try to follow if you are attending. Thank you. So this IF is nothing but interstitial free steel. What is interstitial site? Let's say if you have atoms arranged like this, right? So you have some kind of interstitial voids here. This is called interstitial void. This interstitial void. Interstitial voids. If you place some alloy, if you put some alloy into the pure material, this material, that alloying material are some, I mean, alloying materials are carbon and nitrogen. To improve the strength, now they'll add carbon or nitrogen through some heat treatment process. These are alloys, alloying materials, alloying materials, right? So they are saying that we don't have that material. It means that what? Alloying material is sitting in the interstitial sites, interstitial voids. And there, here we are seeing interstitial free steel. This means there is no interstitial atoms there. It means that there is no carbon only. So it's very less amount of carbon or nothing. Either nothing, no carbon, or a very less amount of carbon. So it is very less, no carbon or some 0.00, some 0.03%, very less carbon. So hence, interstitial free steel will have less carbon. That's it. Simply you have to know what is IF, interstitial free steel. If you know what is IF, that is it. You'll know. Logic wise, we can say that it is having no carbon or less carbon. Happily, you can go and take the process because they're asking for the least percentage of the carbon. Okay, good. Now, next. Basis of slip line field theory in metal cutting. We have discussed in the previous slides, no? Happily, we have discussed what was the each theory, right? So we have even discussed this is phi plus beta minus alpha is equal to pi by 4, isn't it? and this is the merchant's theory. Okay, this is Ernst merchant, right? So this is 2 5 plus beta minus alpha is equal to pi by 2, and this is 2 5 plus beta minus alpha is equal to cot inverse k. We have discussed all these things, right? So obviously, this Ernst merchant is for low power. This merchant is empirical relation. Lee Schaffer is based on slip line field theory. We have discussed this in the initial part of our session today. Simple, straightforward question. Okay, good. Next. Next, in grinding wheel specification WA36K8BBE, what is WA meaning? Wow. So people often people make mistakes. Should not make any mistake here. So the thing is that you have to remember that grading system. So grinding wheel is having some wheel specification. So that is what is this. That is what is this. So what is this? The first one represents the abrasive type. The first one represents the abrasive type. If it is A, it is aluminum oxide. If it is B, it is some boron carbide. If it is C, it is some silicon carbide, like that. Okay, this is some company's specification. Company's specification. A prefix. Maybe it is the in the ledger, maybe in the entry level, it might be the column number or maybe row number, something like that. Some prefix is there. Company specs. This also is manufacturer code. You remove that. The important part is lying in between. Okay, the important part is lying in between. The first one is your abrasive type, and second will depend upon the grain size. See, in grinding wheel, what we'll have? We'll have some abrasive particles like this, abrasive particles like this, right? And there is some bonding material in between, right? Bonding material, some kind of a bonding material, and there is some voids also in between. Bonding material that is there. So this is your bonding, and this is your abrasive particles. Abrasive particles, right? So okay, this is grinding wheel. Okay, grinding wheel spec. Grinding wheel looks like this. Why grinding wheel is used? Grinding wheel is used for finishing processes, right? Based on the abrasive side, bonding material, all these things. No, you get different type of finishing on the product that you are manufacturing. Okay, so the grain size, if you are having a number from 10 to 24, it is coarser grain, big grain. The grain what we are talking here, the abrasive particle. So here abrasive particle is what is grain we are talking about. So very big grain size like this, very big abrasive particle. Medium, this range is medium. This range is fine. The number denotes whether the abrasive particle that you are using is coarser, medium, fine, or very fine. As you are increasing the abrasive particle, super finish will come, because bigger size, no, you will not get good surface finish. If you take a very small grain structure, good surface finish will come. Right? Next is grade. So grade is nothing but the kind of grinding wheel it is. Softer grinding wheel, medium grinding wheel, harder grinding wheel. Okay, that is the A to Z. You have notations. And structure is dense or open. Okay, I'll talk about structure. Let's say I will take this thing as zoom here. Let's say I'll take only two particles. One particle is here, like this grain. This is grain. Another particle is grain, right? So the distance between these two. Okay, let me draw it again. Bigger one. So if this is the thing, if this is your grain, the distance between these two is your structure. It means that the distance between two grains or two abrasive particles is called structure. If the structure, if these two are near, if these two grains are near, then it is called dense. If these are farther, then it is called open. Why, sir? Why it is happening? Having this denser and open, denser will be useful for brittle materials. Why? Because you have small chips. Open is used for ductile materials. Why? You have continuous chips. If you have continuous chips, if these are having very small distance, that is denser distance, the chip will curl and it will get stuck here only. That might affect your grinding wheel specification. It will reduce or it will degrade the grinding wheel if you're using the dense for ductile materials. Okay. And last one is bond type. Last one is bond type. What is bond type? Yeah, yesterday we have discussed vitrified bond, silicate bond, rubber bond, resonant bond, shell-like bond, and shell-like bond is the softest bond that we have seen, isn't it? Yes or no? Vitrified bond is very commonly used bond, right? No. Silicate bond is softest. Sorry, silicate bond is softest. Shell vitrified is commonly used bond. We have discussed in the previous session. They have asked which one is the softest bond. So the last thing says the bond type. So let me remove all these things here. So you just understand clearly. You see what is what here, and you can understand what is there here, right? So now we'll go and see what is the question asked, right? So this is what abrasive particle, abrasive type. Abrasive type we have discussed just now, and the number varies from 10 to 600, right? This 36 is grain size. This K is some kind of grade, whether the wheel is hard, soft, medium. 8 is nothing but this structure. 8 is dense, 0 to 8 is dense, 8 to 16 or 8 and higher or 9 and higher is the dense or open structure, right? And then you have some VB, and that belongs to some bond type, bond type, bond type, vitrified, silicate, all these things. And the last number is manufacturing specification, manufacturer, specs. They're asking what is WA? Obviously, it is abrasive type, and the type of abrasive is C. Isn't it? Yes. Please remember this. It's a very good question. But yeah, you have to remember there is no other option how you can say, sir, like you should know and you should remember this. Yes, you have to remember. Yeah, good. Sorry for this. Sorry, just 1 minute. I don't know. Hmm. Please, 1 minute. Okay, let's go to next question. In metal forming, ring compression test is carried out to find out. First, we have to know what is ring compression. Then only we can know what it is used to find out. What is ring compression? Just keep one ring. What happened? Oh, I didn't paste. Okay, ring compression. Okay, so we'll write here only. Okay, so you take a ring. You take a ring. This is a ring with some kind of a ring. Okay, it is a ring. When I'm not drawing it 3D, so this is a ring. You have a hole here. You have a hole here. This is a ring. Okay, this is a ring. The top view is like this ring. This is ring. Okay. Now you take the ring. You take the ring and put it under dice, something like this, and then compress it. If at all, this is the place of material, and this is the hole, right? This is material of ring, and this is the hole of ring, right? If you're applying the load, then what happens? Then the middle part will become like this. This is because the low friction between the surface and the die. This is die, no? This is die. Sorry, die. This also is die. This also is die. Right? So as it is doing like this, it means that there is a good lubrication, low friction, they say. The diagram is like this, low friction. And if your material is looking something like this, I'll show you that also. Okay, if it is looking something like this, okay, that is, it is something like this after compression, ring only. This is like the cross sectional view. Please do understand that this is a cross sectional view. This is die, die. Right? So now here it means that less friction, so high friction. Right? Low friction means good lubrication. You have good lubrication, that is we have applied. And high friction means less lubrication. So through this test only we can find out the interface friction. Whose interface? Die and the workpiece. Compressive strength is nothing but simply you just it is a maximum stress that material can withstand. So by compression test, especially ring compression test, no, they are saying ring compression. Simply compression test, okay, but ring compression test they are saying no, it is used for interface friction. Upset ratio is no way related to all this test, man. Upset ratio is nothing but the ratio of final height to the original height of the workpiece. It is just the height difference. Okay, so interface friction is the right answer. Okay, good. Next, uh, profile for profile controls, datum is okay. First, what is datum? Datum is some kind of a reference. Datum. They say it's a reference from where you do some experimental start. You say that like yeah, where are you? I am 100 meters. 100 meters what? From where? That is what is datum, right? So the datum is kind of a reference system. Reference system. Right? They're saying that for profile control, what profile control, which profiles? It's like it's only about, let's say you have some kind of a gear gear profilometer. You have some kind of a CNN machine, coordinate measuring machine. You have like that. You are trying to see the profile of the CMM coordinate measuring machine. So this is the involute profile, right? Now they're asking for this profile controls, datum is required or not, or allowed or not. They are saying either it is required, whether it is not allowed but it not required. They are saying, okay. So this will come under this, tolerancing, geometric dimensioning and tolerancing for 2D and 3D structures. Okay. So datum can be used in conjunction with profiles, but it is not required compulsory. That is what is important. See here, coordinate measuring machine, there is no need of datum. Directly it will touch in 2-3 points, tongue will touch. Then from there it will calculate the map and then you can do it. Yeah, if you want the coordinates to be measured, you can put the datum also. So datum is allowed, but compulsory it is not required. That is the answer. Okay. So it's not mandatory. That's what they are saying. They will whatever the CMM, this profile control systems they are doing it. No, they say that this measurement can be done independently independent of any datum. It can be done with datum without datum also we can do. So that's why allowed. I can allow if okay if you are giving okay give me, but it is not mandatory, not required. Okay, so that is the answer. Okay, good. Now, next. Riser is used so as to freeze after casting, freeze before casting freezes, freeze at the same time as casting, minimize the time of pouring. First, we have to know what is riser. Then we'll see why it is used, and then we have to see who should freeze first, or both are freezing at the same time. We have to see that. Okay. So for that, I have diagram already kept for you. Okay, so here we can see this is your pouring basin, pouring cup also you can say, and this is your sprue, down sprue. They can say down sprue, right? And here whatever you are seeing is runner, right? And this is what is your riser side. They say side riser, but also it is known as blind riser. Blind, it is blind because you cannot see that riser. That's why it is called blind riser. That's it. Okay, and same thing. And this is your mold cavity. Now I'll tell you. Pouring cup is used for to reduce the turbulence of your molten liquid that you are pouring, because it will first pour here and slowly it will come like this and go. Down sprue is used to avoid air aspiration effects. Okay, because when you're pouring, if pressure is becoming less here at this point compared to the pressure, if the pressure at this point is becoming less compared to the pressure at this point, there might be some air that is sucked into this point. That air is getting traveled inside the mold cavity here, and then air bubbles are formed. That's why, to avoid that air aspiration effect, we will design the sprue in a tapered way. And then we'll go into the runner, and runner will have some kind of different functionalities to reduce heat transfer, to increase the heat transfer and reduce the turbulence. Like that, they have some functionalities of the riser runner, and then it will rise into this, and then it will enter the casting. Here also it will go, enter into the casting, and then it will go into the riser up. So now what is the purpose of riser? The purpose of riser is to provide the liquid metal if you have some shrinkage that is happening in the mold cap, while the solidification of your product, right? If at all you are pouring some liquid metal and this is being solidified, so if you are having some part, if it is solidifying, when it is solidifying, it's a natural phenomenon where the volume will be reduced. Then who will compensate that, right? So there is some shrinkage that is happening in the casting, shrinkage of casting. So there are three type of shrinkages. One is what? Liquid shrinkage, solidification shrinkage, and solid shrinkage. Okay, so these two, in these two, your metal casting, the casting that you have poured are in still liquid or semi-liquid state, right? But here it is solid state, right? So when you are having liquid state, you can still provide. So in this stage also some shrinkage is happening. In this stage also some shrinkage is happening. So in the first, in these two stages, 1 and 2, this shrinkage will be happening. That shrinkage you have to provide liquid only, and that liquid can be provided by this riser. Okay, but once after it is solidifying, you cannot provide any extra material, so that we will put extra compensation, right? Some allowances will put, machining allowance, draft allowance, so shrinkage allowance, like that we put, and that shrinkage, that allowances are provided on pattern. Okay, those are provided on pattern. Okay, so now tell me, who should solidify first? Casting should solidify first, then only riser should solidify. If at all riser is solidifying first only and casting solidifying second, let's say, if casting is getting shrinked, then who will provide the liquid? Already riser is solidified, no? So riser should solidify after casting, or riser should solidify, casting should solidify before riser. So let's read the options and see what is right. Riser is designed so as to freeze after casting. That is right now. Freeze after casting. So riser should freeze only after casting freezes. Before that, There is no point of using riser. Okay, so freeze after casting. That is the right answer. Freeze before casting is not possible. Freeze at the same time also is not good. Minimizing the time of pouring. So that will be coming under the gating design. It will not depend upon the riser design. So riser is not used for minimizing the time of pouring. Okay, good. That is explanation. Hope you got this. Next. Oh, okay. This is the end for the 2017 manufacturing. I think we'll go for the industrial and operations research. These are two questions, but I don't know. Second question is belonging to material science only. But anyways, like let as PPT is prepared, then we can proceed like this only. Okay. So ABC inventory control focuses on those what? But first, what we have to understand what is ABC control. First, we have to see what is ABC control. So ABC control, ABC analysis, ABC inventory analysis, ABC inventory analysis. Then we'll see what is options. Let's not see the options. Let's discuss the concept first. It is having category A. I'll write cat A. Cat B, category B. Cat C, category C. So what is this? The inventory is nothing but the items that you are putting in your garage, you are saving them for the future use, right? So in that also you are categorizing into some categories A, B, C, isn't it? So generally high value products, high value inventory items will be going under category A. So high value products will be minimal. So 15 to 25% of products will be gone here. High value products. But the high value products will be used for the usage. This is value. And the usage is around 60 to 75% of the usage. Category B, the value is some 20 to 30. And the usage is are also very less usage, 20 to 30% of usage only. And the value is 40 to 60%, and the usage is less. Okay, so value in the sense the percentage of items. The percentage of items are 15 to 25, usage is 70. The percentage of items is 20 to 30, usage is 20 to 30. The percentage of items are 40 to 60, and the usage will be around some 10 to 15. Okay, so now this is what is ABC control. So high value inventory, medium value inventory, low value inventory, right? So that is how this inventory of ABC is managed. Okay, so now let's read the question. Inventory control focuses on items not readily available. Obviously, see why we'll put some things on inventory is not inventory means which are readily available, right? So items not readily available. How can you make it this inventory? Wrong. In items which consume less money. So items which consumes less money is in the category C, but we are mostly in usage is more here, no? The usage is more in the value is more here. So the usage is more in category A. So items which have more which consumes more money is what this focus will happen, because these two are automatically happening because more usage is happening at 60 to 70. So your focus should be on this category A. As your focus is on category A, the items which consume more money will be concentrated by ABC inventory control. That is it. Okay, item option B is the right answer. So this types, although these are very low quantity, 15% of right inventory is less, but still they account majority of inventory cost. 60 to 70% of usage is there. No, that's why it concentrates on which consumes more money. Okay, that's good. Very good. The last question for today is this. What is that? Knife line or hairline cracking is observed in ferritic stainless steel, martensitic stainless steel, austenitic stainless steel, and stabilized stainless steel. So for this, you have to understand proper uh, material science while cooling. So we have to understand the iron carbide diagram and the TTT, time, temperature, and transformation diagrams. These two diagrams, if you know, then most of the questions can be answered. Okay. So what is this ferritic stainless steel? These are ferritic steels generally as having this alpha ferrite and all. So these are not very hard. Very hard materials are where the carbon content is more. Ferritic is that alpha is ferritic. So there you can see, because if you yesterday we have seen, so the hypereutectide, hypoeutectide, like that we have seen the carbon percentage is 2.3 somewhere here, where we'll do it at 0.8 only. So here less carbon, no cracking. Cracking will happen only we have the hardness. When it is increasing the hardness, the cracking will happen. But obviously ferritic steel will not have any cracking. Okay. Martensitic steel is hard, yes, but another important the property of martensitic steel is toughness. This is tough because of its structure property. Okay, BCT, body centered cubic, body centered tetrahedral. We have seen now today only. So obviously, as it is tough, no, obviously it will not have that hairline cracking or lifeline cracking. And austenitic is also having less carbon compared to whatever the stabilized one, whatever we are seeing here. So austenitic steel also is good for resistance, corrosion resistance. This is good for corrosion resistance. Corrosion resistance. So here also there is a minimal chance of this hairline, or there is not associated with hairline cracking. But stabilized steel is the answer for us. And here, stabilized steels will have some kind of elements like titanium, niobium, some kind of stable carbides are added. Even some chromium carbide, something like that, there are added some extra additives are added, so that you have this stabilized stainless steel. Okay, so internally, if I can say, there'll be some kind of grain boundaries. There are hitting with chromium intergranular corrosions. There are so many terms. Let's not go in deep into that. For our understanding, we can say that because of the uh, 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 some corrosion that is happening at the grain boundaries because of the additives that you're adding, hairline cracks can be seen in stabilized stainless steel. Okay, so that is what is this. So I think we have completed this session a little earlier because we do not have numerical questions today. Although we have 21 plus 2, 23 questions, we have hardly one or two numericals. Mostly it is theory based. So maybe ISRO guys have thought that it is taking more time to solve the numerical questions in the previous year 2015 and 16, and they might have reduced them, and mostly they made it theoretical and conceptual questions. Okay, so you visit the lecture, listen to the lecture, and see if you have any doubts. Please ask that in the YouTube chat, and we'll be able to answer them wisely. If at all, you can contact take the number of mine from the institute, and we can discuss even in the phone call also. Okay, so thank you for attending this session, or listening this session, or viewing this session. Let's meet in the next session discussing the set 2 of 2017 ISRO question paper for manufacturing and industry. Thank you.